Welcome back to Chapter 8 of America's Boating Club's Sail Course. In this chapter, we'll be covering balance, boat balance. Boat balance is the ability of a boat to stay on a steady course with no pressure on the helm. When a boat is underway, it's really propelled by two counterbalancing forces. The wind, the force on the sails creates a lifting force that propels the boat forward, and it's offset by the hull design in the underwater boat that prevents it from sliding sideways. These two forces can be consolidated into a single point on the sail, one being the center of effort, which is pushing it forward, and the other being the center of lateral resistance, which is holding it from going sideways. Where these forces are located, these points, determines how much balance the boat has. If they're in equilibrium, the boat will go forward, and if they're out of balance, not in equilibrium, they will tend to cause the boat to turn one way or the other. In this example, we have the wind force, which is pushing in this direction at the center of effort, and then we have the water force, which is resisting the tendency of the boat to slide sideways, which is the center of lateral resistance. Depending upon how well the balance are, we have to then turn the rudder angle to offset whatever is not in balance. Here we have two different pictures of weather helm and lee helm. Helm refers to the position of the tiller or the wheel, which causes the boat to turn. A boat with weather helm if you let go of the tiller, the boat will turn into the wind, will tend to turn into the wind. A boat with lee helm, if you let go of the tiller, the boat is going to turn away from the wind and then actually get more power built into the. If you had to choose between the two, weather helm is a little bit better than lee helm. The advantages of weather helm is when you let go of the helm, such as if when I fall down and drop the helm, the boat will turn into the wind and it'll then stop. It also provides a little bit of a hydrodynamic lift to create the sail forward. If we get hit by a gust, it'll cause the boat to round up and then spill the wind, which then depowers everything. It's also less tiring on the helmsman to pull rather than push the tiller. And I think it provides a light feel of the boat and when we're sailing. The disadvantage is if we have too much weather helm, it actually acts as a brake because it creates extra friction or drag back here on the back if you have to pull on the tiller more than a lot, and it also causes the rudder to stall, making it hard to steer. Lee helm is a little bit dangerous because it can actually lead to an accidental jibe. The forces generated by the sail can be consolidated down to a single point of the sail. That would be the geometric center of effort. This geometric center of effort can be calculated by running some lines from the center of the foot up to the head, and then also from the center of each side to the opposite corner, and where they intersect, that is the center of effort. If you're out on a boat, if you look up from the middle of the boom towards the top of the mast, about a third of the way up the sail would be approximately where that geometric center of effort is out on the water. It was pretty easy to determine the geometric center of effort on a single sail, whereas a main and a jib is a little more complex. We're going to find the geometric center of effort of each of the sails like we did if they were by themselves. So here is the geometric center of effort for the main, and here is a geometric center of effort for the jib. The next thing we're going to do is draw a line between those two centers of effort. Next, we're going to draw a line perpendicular from the center of effort of the main away, and then we'll also draw another line perpendicular to that away from the jib center of effort. The length of these two lines are going to be proportional to the square footage of each sail. So in other words, the length of A is proportional to relates to the jib square footage, and B, the length of B, relates to the same scale as the mainsail square footage. When we've got those two lines driven, then we connect A to B, and where it crosses our line between the two center of effort, that is the center of effort for the two sails combined. The last slide looked at the geometric center of effort. And that center of effort, again, is the central point of the sail where the forces are combined into one point. That would be the center of effort, and there would be a spot here on the sail about a third of the way up that reflects that. To counteract that force, we have a center of lateral resistance, which is the central point of the underwater surfaces where all the forces are combined. And so that would be counteracting our center effort. We've got our center of lateral resistance. The sideways lateral force of the center effort is resisted by the forces on the underwater surfaces, the center of lateral resistance. If we didn't have this lateral resistance, sailboats would just be blown across the water like a leaf. The geometric center of lateral resistance can be illustrated using a cutout of the underwater portion of a boat. Here's my profile of a boat that's out in the water that we're going to use for our demonstration. Now, if we take and add on to this white part here is the underwater portion of the boat, and that's where we're going to try and measure our center of lateral resistance. So if we take this profile and we find the balance point of that profile, that would be our approximate area for our center of lateral resistance. So in this case here, we have it balanced on the point, and that point where I was balancing it, that is our geometric center of lateral resistance. Now, the exact location of the center of lateral resistance and center of effort is really not important while we're out sailing on the water. What is important is to understand the relationship between the center of lateral resistance and the center of effort as we try to determine how it affects our helm. At the design point, the geometric center of effort is always forward of the CL center of lateral resistance, and this causes it then to take on some of the advantages that you have with a little bit of weather helm. Those advantages are that when you let go of the helm, the boat will turn into the wind. Based upon where the center of effort and the center of lateral resistance are, that will determine what direction the boat turns if the rudder is held straight. We've got really three examples here. We've got our weather helm and our lee helm. If we move the center of effort back, aft, from the balance point over here, that will cause the boat to tend to turn into the wind, and we would have what is called weather helm. If we move the center of effort forward, that will give us it will cause the boat to tend to turn this direction, and that would give us the feeling of lee helm. And we have to then turn the rudder to compensate for that as we're trying to go straight. The center of effort and center of lateral resistance are both very dynamic because they change when the boat is underway. When they're underway, the center of effort and the center of lateral resistance move forward. As it moves forward, the center of lateral resistance moves forward more than the center of effort. The center of lateral resistance also moves faster than the center of effort. The center of effort, that in the sail, is the greatest at the luff and is least at the leach, and we'll cover that in a future chapter. Again, the actually being able to define the center of effort and the center of lateral resistance is sort of a theoretical point. What we really want to be able to do is identify what techniques are available for us to change where these locations are. Center of lateral resistance is going to remain pretty much fixed on a boat, but the center of effort, we can change that with different adjustments with our sails and our weight while we're out on the water. And that's what's really important as we try to figure out how to create the best, most neutral helm that we can. There are other factors that affect the balance of the boat. The center of effort is not on the center line of the boat because the sails are on the leeward side of the hull. This creates a yawing moment. A yawing moment, again, is the moment that tends to rotate about the hull on a vertical axis. So the yawing moment is going to make the boat go like this. It's usually due to the way the center of effort is on the outward side of the center of lateral resistance. This forward driving force, D, is not on the center line, so that because both sails are on the leeward side. The resistance R, that's the resistance of friction, the resistance of the water, is on the center line. And so the distance between R and D is the yawing moment arm. We can reduce that yawing moment when going downwind by using a spinnaker or by sailing wing and wing. By sailing wing and wing, we would have the jib over on this side, which would then we'd have part of our center of effort on this side and part of our center of effort on that, and that would reduce the yawing moment arm. In the previous slide, the sails were set up to be close hull, and so we could see that the sails were very, run in tight against the hull. In this case, we're dealing with a broad reach, so our sails are spread out, let out farther to match the direction of the wind. In doing that, you can see that our center of effort has shifted even farther to the downwind side, because our center of effort is in the middle of the sail, and as we let that out, it changes the center of effort outward. And what that does is it changes this area here between the resistance and our driving force, which makes our yawing moment arm even larger. This yawing moment arm would be often seen when we're going off the wind and we get hit by a gust, which then causes the boat to broach. And the broach is to turn unexpectedly. So the extra wind would push on this, creating our yawing moment, which then causes the boat to turn out of control. This slide illustrates the effect of heeling on the center of effort and the yawing moment arm. If the boat's sailed flat, our center of effort is in the middle of the sail and creating our moment arm this wide. Our center of lateral resistance is in the center of the boat in both cases. Now, as the boat heels, you can see that center of effort has moved over to the leeward side a little bit more, increasing our yawing moment arm, which then makes it subject to broaching like we talked in the previous slide. While we're sailing underway, we have several things we can do to correct weather helm. In this case, we're talking about things that can move the center of effort to reduce weather helm. One of the things we can do is we can move the main sheet traveler to leeward, let it drop down a little bit, and that will reduce the center of effort of the main and let the jib be more powerful relative to that balance. We can also ease the main sheet slightly, which would then also reduce the center of effort in the main, or we can trim the jib a little bit more, which would then put more center of effort in the front of the boat that would put more center of effort in the front of the boat. We can also reduce the angle of heel by hiking, which then brings the center of effort more closer to the hull and would reduce that effort. And another thing we could do is we could rake the mast forward. This would require a bit of a standing rigging change. When I'm sailing my Thistle and want to reduce the weather helm, I'll do one of two things. I'll either try and get the hike more. I need the crew to hike more because I'm already too old to do that. Or we could ease the main sheet a little bit. If you ease the main sheet, that would cause the boat to flatten out, and then that would also reduce the weather helm. There are some things we can do to change the center of lateral resistance to reduce our excessive weather helm. One of the first things we could do is move our weight, our crew weight, back. That's going to cause the boat to be a little heavier on the back, which would then reduce our CLR. Also, if we move the center board partway up, what that does is it tends to tip the boat, move that center of lateral resistance back in the boat just a little bit, which would then help balance out the weather helm. Some other causes of weather helm is if our foresail, our jib, is too small, and that doesn't have enough center of effort in the jib to offset the center of effort of the main, and that would create a weather helm feeling. If our main is too large, again, it's not in balance with the jib, and so it would create weather helm. If we had the mast rake going too far back, that also moves the center of effort too far back. And just the opposite thing is if we've got the center board too far forward, that would cause the center of effort, center of lateral resistance to be farther forward than we would like. I think the key point of these last two slides is really to look at what are some of the things we can do while we're sailing to help balance our boat out more, because the boat balance is really enables us to get the most power translated into forward motion that we can. If it's out of balance, then we're going to be using power inefficiently. Let's take a peek at the vocabulary for this section. When we talk about beat, we're talking about a close-hauled course going upwind. A bit is a post on the deck somewhere that's very secure that you can use to tie lines for towing the boat. Rake is the slope of the mast from vertical in a fore and aft direction. A reach is the point of sail between close-hauled and a run. Running is when have the boat going downwind with the wind directly astern. Our waterline length is the measurement along the waterline from where the bow touches the water and when the stern emerges from the water. The yawning moment is the moment that where the boat rotates around a vertical axis, usually because of a change in the center of effort on the outside of the boat. This concludes section 8 on balance. Our next section will be on the wind.